Hi, welcome to my first Code with Me episode. Let me start off by telling you what this new series is all about. The main goal is to create a relaxed environment where we can just code together. So, what I'll do is I'll start off by telling you what I'm going to code. I'll tell you my plan on how to implement it, the structure I've created, and then actually code that particular concept. And you can open up an IDE that you like and try and code it yourself too, along with me, and let me know if you think of a different approach that might work out better. I'd love to know. Please put it down in the comment section. That's the main aim of this video series, just to have a lot of fun coding concepts that we have discussed in other video series. So hence, these episodes will not be released weekly like it has been for the previous two series. The reason, as I said, was because the intent is to implement something that we have already discussed. For example, my most recent video series was on deriving R square, and in that, I talked about simple linear regression, and we had discussed different examples, how data is used, and how to calculate R square, what R squared is. So I thought, why not actually implement whatever we had discussed at that time? Okay. Okay, so let's start off. My preferred place to code. I'm very fond of Sublime Text. No particular reason for it, just that I like it. Okay, so I usually use Anaconda prompt along with this to run my Python files. And just to let you know, in case you're not familiar with this is Python. I'm going to be coding simple linear regression in Python, and I'll first tell you a couple of things that I've already, if you notice, I've already created a basic structure. So let me just show it to you once. Okay. Now, don't look at everything else, just look at this line that I'm going to highlight. If you notice over here, I'm reading a CSV file called TV marketing. I found this data set on Kaggle. Let me explain a little bit about this data set first. The data set is so the first column, which is the predictor column, is about the budget for TV marketing. So basically, it's about a place that wants to sell TVs, and they're trying to understand how well what is the relation between the budget for marketing TVs versus the sales that come in. Okay? Now, you may have a doubt, in case you've studied these concepts earlier, that what about normalization? So, what I've done is, in this particular case, I've taken a data set that doesn't require it. And also, because we are using simple linear regression, it no predictor will get more weight than another predictor. People who have not studied about normalization will not understand this sentence, but I will talk about this concept in more detail in the videos to come. Okay. And one more thing about this data set is this, that I'll put in a link in the description box to the data set, and you could probably download it and use it yourself. Okay, that was the first thing. Second thing is, if you notice over here, I have imported the NumPy library. I have two reasons for this. Okay? Number one, and the main reason, is that NumPy arrays are just faster. The reason for that is, so faster, I mean compared to Python lists. The reason is this, I'll tell it to you in one sentence, and I hope to create a full video on this concept too. The reason is this, that in a NumPy array is created using C++. So what happens is, when you access a certain element of the NumPy array, you're directly accessing that element. So all the elements of the array are in contiguous memory locations. Okay? And what happens in a list, in a Python list, is that you go to a certain element of the array. So the way the array is stored in the memory is this, that It's first a set of continuous memory values as an array, and then so you require two memory accesses to even reach the actual element. And that is the reason why different data types can be stored together in a list, unlike arrays. So I'll talk about it more in more detail in other videos. For now, you just need to know this much, that it is much faster, and along with that, it has been created to work well for matrix multiplication and other matrix operations. So, because what we are going to be doing is to implement um, all the concepts we talked about earlier on actually multiplying each y and x value and stuff like that, we are going to use matrices. Okay, so that's the intent of using the numpy library. Pandas has been used, as you saw, I read the data frame using this library. And matplotlib, I have also created an extra function just to plot the data along with the ask, the best line, the ask square line, the regression line, whatever you want to call it, just so that we have an understanding of how that thing even works. Okay, now let me tell you the structure of the code. So the structure I thought of was this, that I create a class on simple linear regression, and in the constructor function or the initialization function, um, I initialize instant, I create instance variables that are reused a lot in different functions. That way we don't have to return and we don't have to return the values and reset the values and stuff like that. That was my thought behind it. And that way, even if an object is created and it just wants to access that particular variable's value repeatedly many times, it can, because it's the instance variable. Okay. Okay. Now what you'll notice over here is one more thing. I have structured many functions. I still haven't filled them up. I'll fill them up with you. But you'll notice a lot of functions. The reason for creating a lot of functions is actually a great tip that was given to me by my seniors while I was working. I used to create long functions, okay, lots of things happening in the same function. But I was advised to create functions that have exactly one functionality. The reason for that is this. Now think of it in this way. I'll tell it to you very briefly. That let's say if I combine three functions together, okay, calculating sum, calculating mean, oh, so sorry, calculating the sum, calculating the mean, finding MNC all together. But now what if I create an object of this class and I only want to use that object to calculate the sum? I don't want the other two functions to work. I don't want the functionalities to happen. I won't be able to do it, right? That is why what they say is create functions that are very specific in nature so that they can be reused. Hence, the main reason is reusability. That's it. Okay. Okay. You may have a different thought on this. Do let me know your thoughts. This is something I've seen. Uh, I've practiced this and it has been very useful to me. Okay. So now let's start with the actual code. If you notice over here, I did read a pandas data frame and I passed it as an argument to the initialization function over here. Okay. Now, if that is a pandas data frame, how do we get numpy arrays from it? So if you notice, this first line of code I've created is also numpy array. They call it an ND array. So I may use ND array also in between, this term in between. So if you notice over here, I have taken the first column of this data frame and data frame in the sense data set, okay, in case you're confused. And I've just extracted the values. Now by doing this, by writing dot values, I change it into an ND array. Okay? You can think of it in that way. So now my X and Y are actually ND arrays. If you notice, X is the predictor variable. That means over here it is the budget, marketing budget. Y is the predicting, or the value we are trying to predict, and over here that's the sales made. Okay. One more thing you'll notice over here is this, that I have initialized something called n. I've created an instance variable n, which is the length of, or it will tell you the number of elements in X. Now, why I haven't even talked about Y is, it's a very simple reason, that X and Y will have the same length, because each predictor is connected to its predicting, right? They're all pairs, unless of course there are missing values which this particular data set does not have. Okay, so let's continue. We'll keep talking about each one of these as and when the time comes. Okay, so the first thing is, if you notice, the first function I've created is calc sum. Reason is I want to sum up every value in the X column versus every value in the Y column. These sums are eventually used to find out M and C. If you have watched the video series, you'll understand how it is being used. Okay, so let's start. If you notice, I've even created instance variables for this. So self.sum x equals. Now I'm going to use a very interesting function called sum. It is a part of the NumPy library. And what this does is um, it sums up every single element in a particular column. Okay, you can also make it sum up a row, but you'll have to change the axis. You can check out the syntax on the main NumPy website. It has all the information over there on how you can do the different things. Okay, so first we want to sum up everything in X. Now, this is where another thing comes into play, that when you sum up everything, what happens is it creates a 1x1 array, means just a single element in the array. So 1x1. And what happens in that case is, you'd probably guess it, that if you have an array, you cannot use it as a scalar value. That's why what you do is you use this thing called item. It's a function which helps you get the scalar value from this array. Okay? So you'll do the same thing for y. Okay. So now we have the sums. Next, we need the means, because that's also going to help us. So let's do it in a similar way. Now I'm going to use self.sum to help out with this. Now this is where you'll see for the first time I've used self.n. That's why it was very useful to create it in the starting itself. Okay, and this self.n will be used a lot. Now if you notice, because some x and some y are already scalars, it's very easy to divide it by n and then assign a numerical value to mean x and mean y. Okay, so now we have mean x, mean y. Next, we need to calculate m and c. That's the main thing, finding out the two coefficients. Now, if you notice over here, I've just written down the formula so that we can code it easily. So this is the formula I derived in the video series itself. There are ways of reducing it further into covariance of x comma y divided by variance of x. But because I didn't talk about that part, I am staying with this formula we talked about. Okay. Now if you notice over here, there are two more things required. Sum of xi yi, which means multiplying every corresponding pair of elements in the x and y arrays and xi square. Okay. Now these two values are not really used anywhere else, which is why I thought of not creating them as instance variables, but instead creating them as local class variables just belonging to this particular function. Okay, that was my thought behind that decision. Okay, so let's first do that. Now the first thing is, before we can find the sum, we first need to multiply all the corresponding elements. And here again, NumPy arrays come as saviors because they are so simple to use, and there's this concept called broadcasting in NumPy arrays, which helps you just use normal arithmetic operators to multiply to do so many things. Let me show it to you. So over here we could just write self.x times self.y. Now x and y are ND arrays, but by putting the multiplication sign in between them, it indicates that every corresponding two elements have to be multiplied to each other to result in one single array, which is so cool and so makes life so easy, genuinely. Okay, now let's create the sum for xy. Okay, so over here we again use np.sum. Now similarly we need x square, so we'll do that. Okay, so now we have everything we need. Let's find out m. So first we look at only the numerator. The numerator says sum of xi yi. So we have sum xy minus sum x. Wait, this should be self dot sum x times okay. This is our numerator. Let me just add this over here just for the sake of it, but it should not matter because of the PEMDAS rule. The division would have come first anyway, just to structure the code properly. Okay, divided by the denominator, which is, now we already have some square minus sum of xi the whole square, so that is this is constant variable. Okay, divided by okay. Let me just check the parentheses. Okay, let me just create one more just for the sake of it, like earlier. Okay, now that we have m, we can always use c. Once again, let me just recheck this. Make sure that the parentheses are right. Okay. 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 Now let's do it for c too. C is equal to mean of y self dot minus, now we already have m. Oh, one mistake. It should be self dot m Reason, I'll tell you in a second. Okay, self dot c, self dot y minus c self dot m is already being used again. M x. I've made a small mistake over here. This should be self dot mean x. Okay. Basically, you have two scalar values now, self dot m, self dot c, but you will now see how these two values can be finally used. Okay, we have created them, and the reason why we created them as instance variables is it will be used to find the predicted y values. So this line that we have found out, this best line, what are the y values when we substitute this and see? Substitute all the x values on this line. What are the y values then? That's what we want to find out. And I've created an instance variable for this too. It's called ypred. Okay. Now over here, you will notice another thing about broadcasting. So let's have a look at that. So y is equal to mx plus c. So first we multiply m. Now we are going to multiply it with self dot x. So you see we are multiplying a scalar with an array. How do you do that? If you did that with lists, you just get repeated lists of the same kind, just many times repeated. But over here, what it does is in ND arrays, it multiplies this value of m with every single element of x to create one resultant array. Okay? Plus c. Now over here too, you have an array out of m and x, but c is again a scalar. So what will happen is c will get added to every single element of mx. Okay, that's how beautiful broadcasting is. Now just think if instead you had to create many for loops. A huge headache, to be very honest. That's my perception, especially when you're working with larger arrays, and for loops are known to be slower in Python, so it'll just slow down the entire process a lot. Okay. Okay, now let's go to calculating the SSR value. Why do we need it? Eventually find out the value of R square. Okay, self.ssr, we need the sum again, so np.sum. Now we need y predicted minus y mean the whole square. So, okay, I keep forgetting to add the self. Okay. Here you'll see another instance of broadcasting. Okay, here's another one. Okay. So this will be self.ssr. Now we get SST. This is y actual, okay, not y predicted. Y actual means the initial y values. Okay. Now R square. We're almost at the end. Yay. Okay. So now we've come to the end. We've coded everything. Let me just explain this last function to you, which plots the line and the data. So what you'll notice over here is it first creates a scatter plot out of the x and y values, which means you'll see it as small dots, each data point as a green color dot. And what will happen is then this x label line is to just uh, write down what the x values are about, and the y values, this is just like a title for each axis, and then there's a main title for the entire diagram, the entire graph, and this plot function creates the line. So that's why if you see over here, I've put self.x versus self.y predicted. Here it was self.y because we were looking at the actual data points. Here we are only looking at the predicted y values and hence creating a line. Okay. And plt.show basically means show the graph. That's it. Now if you notice over here, I have created an object called model, which which is an object of the Simple Linear Regression class, and I have called each function one by one exactly in the sequence that we created it in. And what I'll do is I'll print the R square value before calling the plot, because otherwise you won't be able to see both of them together. Because once it shows a certain plot, it will stop the rest of the code um, until you shut the plot. Okay. Now my hope is that this will work in the first time, but it usually doesn't. So let's cross our fingers. Over here, I've already opened it up using uh, command line uh, commands, and okay. So let's try running this Python linear regression. Okay. Okay, let's hope it works. Yay. Okay, it's working. And if you notice over here now, why didn't the ask square value show? Okay, probably after we shut it, it will show. So if you notice over here, the blue color points, okay, sorry, I said green earlier, it's actually blue. The blue color points are all the data points, which means that it represents how each data point initially was. What were their x values, what were their y values. And the red color line is the best line that we have found that can represent all of this data. Now something you'll notice over here is this, that this data, if you can see my cursor, it's kind of like a funnel structure, right? Now, why is this very important is that look at this part where the bigger end of the funnel is. For a small, like, okay, look at these 2 points where my mouse is, okay? For a small change in x, the change in y is huge, right? Comparatively, of course, it's relative. Now, the thing is this, that, and right after that, after a small change, there's one very close to the line, okay? So, this is basically saying, and look at this one, okay? It's almost the same x. Oh, sorry, this one is the same x almost, but it is so different in its y values, which means that there may not be a very high correlation between these two variables, meaning that maybe budget for advertising cannot really predict the sales as well as we want it to, because for similar values of x, you're getting very different values of y. This means that using x to predict the values of y will be tough. So let's have a look at the R square value and see if that's any good. So the R square value, as we discussed, if it's closer to 1, it means that it's a fantastic regression line that you've created. But if it is closer to 0, it's a very bad line. Now, usually the accepted values, the ones that say, oh, the model is superb, are like 0.8, 0.9. Those are good values. Okay, so let me just close this there. Now look at this. The R square value is 0.611, and that it collaborates with our not collaborates, that's the wrong word. It basically proves what we were talking about, that they may not be properly even related to each other. So therefore the R square value is also coming out pretty bad, that there is not a very good line that can actually represent the data, and a line can't represent it. Okay, so yeah, that's it for this video. This is mainly what I wanted to talk to you about. If you have any questions on why I did certain things, you can ask me in the comment section. If you, as I told you earlier, if you have any different approaches, if you have different ideas, or you have suggestions, please let me know. I'd love to learn from you. Okay, then. Hope you have a great week ahead. Bye bye.